Yes, good morning, dear students. I'm once again here to continue with hydrocarbons. I remember in our previous lesson, I'd looked at the introduction to these compounds, and I looked at the functional group in them. Functional group in hydrocarbons is the carbon halogen bond. So if it is chlorohydrocarbons, it is the carbon chlorine bond. That's the functional group in them. And it attributes the reactivity of these compounds to the reaction they undergo. So we looked at the general formula of those that are monosubstituted and are aliphatic as CnH2n, and then 2n minus 1x, whereby one hydrogen is substituted by a halogen atom. X can be commonly chlorine, bromine, or iodine, and sometimes or rarely fluorine. We also looked at hydrocarbons being primary, you remember that, secondary, or being tertiary. And we looked at examples. When is it primary? When one of the hydrogen atoms in an alkane is substituted. When is it secondary? When two of the hydrogen atoms in a haloalkane are substituted, or when the halogen atom is on a carbon containing only one hydrogen atom. And when it is tertiary, when all the hydrogen atoms of a certain carbon atom are all substituted, like in 2-methyl, 2-chloro-2-methyl propane. So we looked at all those examples. I also looked at hydrocarbons being saturated or unsaturated. When are they saturated? When you have only single bonds in them. When are they unsaturated? When you have at least a double or triple bond. And I gave you the most common unsaturated hydrocarbon, which is 2-chlorobuta-1,3-diene, a useful monomer in the formation of rubber. Remember me emphasizing that. I also looked at hydrocarbons being polyhalic or polyhalides. Those ones that have more than one halogen atoms in them. For example, I looked at ethane, 1,2-dichloroethane. Another example you can have is this example here, 1,2-dibromopropane. And we said that the moment you have the halogen atoms on adjacent carbon atoms, such a polyhalide is useful in the synthesis of alkynes. Remember that important introduction. We looked at trichloromethane, tetrachloromethane, all those are polyhalides in which one or more halogen atoms are present in the chain. I also looked at hydrocarbons being vicinal or germinal. When are they vicinal and when are they germinal? The vicinal ones are those in which the halogen atoms are attached to adjacent carbon atoms. The example is the one which I've already written here, 1,2-dibromoethane. That is a vicinal dihalide. When are they germinal? When both the halogen atoms that are present are on the same carbon atom. Like this one here, which is 2,2-dibromopropane. It's a germinal dihalide. Germinal dihalide is also useful in synthesis of alkynes, although they are rarely used. We said both vicin and diaminoside can also be used in the synthesis of alcohols, diols, by substitution of the halogen atoms with the hydroxyl group from sodium hydroxide solution and on heating. You remember that. Then I looked at the nomenclature of aromatic halides, which we call aryl halides, like the chlorobenzene, the bromobenzene, iodobenzene, and others. And we said you can have them when you have only the halogen atom or when you have another substituent in the benzene ring. We named those in detail. I don't want to go through them again. So I detailedly went through the literature of, the nomenclature. I also took you through the isomerism. For those who were not present, you'll tap into my inbox and ask about that. I made a brief introduction about the physical properties, but it does no harm reminding you what we said about them. The first physical property I looked at was solubility. I told you that hydrocarbons are unexpectedly, it is so surprising that they are insoluble in water. Why are they insoluble in water? Because they cannot form hydrogen bonds with water. However much the carbon halogen bond in them being greatly polar due to the high electronegativity of the halogen atom, making it gain a partial negative charge and the carbon gaining a partial positive charge, they cannot form hydrogen bonds in water. And that leads to their low solubility or almost being insoluble in water. However, they are very much soluble in organic solvents. Organic solvents like benzene, ether, which you sometimes call ethoxyethane, and others. So the reason to their insolubility is attributed to the inability to form hydrogen bonds with water. I looked at that in detail. In terms of density, which is the other physical property, we said that hydrocarbons are less dense than water, specifically the alkyl halides. Alkyl halides are less dense than water. What does this mean? That if you put an alkyl halide with water, you'll find that they float on water. The moment you go back to school, try to ask for carbon tetrachloride. It's an alkyl halide, or chloroform, trichloromethane, mix it with water. You're most likely to see it floating on water. Reason being, they are less dense than water. What causes that low density in water? It's because the molecules in the haloalkanes are closely packed. They have what we call close packing. And the molecules themselves are small. They are closely packed and are very small. So if they are closely packed together, they are so compact and very small. In their liquid phase, must specify that. So that makes them float on water. This is for alkyl halides, most of them. However, there are unique ones. The unique ones are the alkyl bromides. Alkyl bromides and alkyl iodides. Alkyl bromides and alkyl iodides are all denser than water. For example, bromoethane. Bromoethane, if added to water, it will be water to float on the bromomethane. it is denser than water. This could probably be attributed to the high molecular mass and these molecules being very heavy. Bromides and iodides are very heavy due to the then corresponding same chain chloroalkanes or fluoroalkanes. So that's all about solubility. It's all about density. We have said the density, most of the alkyl halides are less dense than water. The reason is due to the close packing and the very small molecules in the liquid phase. The next point I want us to emphasize about physical properties is about the boiling point. So when I talk about boiling point, I'll be looking at comparisons here, or comparisons with other homologous series, or comparisons with the haloalkanes themselves with different carbon chains. Now you'll find that alkyl halides have higher boiling points. They have higher boiling points than corresponding alkanes. They have higher boiling points than corresponding alkanes of comparable molecular mass. Of comparable molecular mass. What's the reason behind this? I can give you an example. If I have maybe chloroethane, CH3Cl, molecular mass of chloroethane is around 35.5 plus 12 plus 3. That is 35.5 plus 12, that is 47.5 plus 3. 47.5, when you add 3, that is 50.5. So if you look for an alkane of almost the same molecular mass, it can be CH3, CH2. Let's look at this. This is 36 plus 8. Let me look at butane, CH3. This is 48. I think butane is even bigger. So you have 48 plus how many hydrogen? 6, 7, 8, 9, 10. Add 10 here, this is around 58. It will be bigger, but the molecular mass is almost the same. I may not have a perfect example here, but if you get an alkyl halide and an alkane that almost have the same molecular mass, you'll find that the alkyl halide has a higher boiling point than that alkane. So a question can be set to you to explain why maybe chloroethane has a higher boiling point than maybe propane or butane. The reason there is because in the haloalkanes, if this is my haloalkane, R is an alkyl group, the halogen atom is more electronegative than the carbon atom. So this halogen atom being more electronegative gains what we call a partial negative charge, and the carbon atom gains what we call a partial positive charge. Okay, what does that result into? It makes the carbon halogen bond very polar. So when the carbon halogen bond is very polar, it enhances what we call dipole attractions. Dipole attractions in the alkyl halides are enhanced, or they become strong in their liquid phase. However, in the alkanes, we only have these bonds. We have only carbon hydrogen and carbon bonds, both of which are non-polar. And there you only have to see weak van der Waals forces of attraction, which are more easily broken. Actually, dipole attractions are also van der Waals forces, but they are enhanced. They are stronger than those in the alkanes. So what shall we say in a brief? We shall say alkyl halides have higher boiling points than corresponding alkanes of comparable molecular mass. Why? In the alkyl halide, if it is specified, you also specify the carbon, the halogen atom If it is the carbon atom, you say the carbon atom is more electronegative. It's more electronegative than the nearest carbon atom. And therefore gains a partial negative charge. Whereas the carbon atom gains a partial positive charge. This makes the carbon halogen bond. Makes the carbon halogen bond polar, comma, enhancing dipole attractions in the liquid phase. However, alkanes have only carbon hydrogen and carbon bonds, which are non-polar, and their molecules are held by weak van der Waals forces of attraction, which are easily broken. So briefly, that's what you can talk about. I hope you're following. Talk about the electronegativity, more electronegative than the nearest carbon, partial negative charge, partial positive charge, carbon halogen bond is polar, dipole attractions in the liquid phase are enhanced. Carbon bonds and carbon halogen bonds, which are non-polar. I think that has been well explained. The other thing I want us to explain is that haloalkanes, still about boiling points, have higher boiling points than alkanes of the same carbon chain. Let me see an example. Bromoethane is a haloalkane. I can have also another alkane called ethane. Bromoethane has the formula CH3CH2Br. Ethane has the formula CH3CH3. The boiling point of bromoethane is about 38 degrees Celsius. The boiling point of ethane is about negative 89 degrees Celsius. I think you notice the great difference. Bromoethane is boiling in negatives. And I told you any compound that has a negative boiling point is a gas. So bromoethane being a liquid, it has a positive boiling point at 80 degrees Celsius. So we need to explain what causes this difference. Why is the boiling point of ethane very low compared to that of bromoethane? Yet the two compounds have the same carbon chain. So this is attributed to, actually both of these are held by van der Waals forces of attraction, which are specifically dipole attraction is bromoethane, and van der Waals forces of attraction, which are existing in ethane. So what shall we say? We shall say that the reasoning here is due to the molecular size and molecular mass that makes the van der Waals forces of attraction in bromoethane stronger. So what will you say? You'll say bromoethane, if you explain the difference, bromoethane has a larger molecular size then it has a higher molecular size and a higher molecular mass. Bromoethane has a larger molecular size and a higher molecular mass than ethane. Therefore, bromoethane has stronger van der Waals forces of attraction. Has stronger van der Waals forces of attraction that require a higher amount of energy to break. That require a higher amount of energy to break than in ethane. I want you to recall that the strength of van der Waals forces of attraction increases with increase in both molecular mass and molecular size of molecules. And that's the reason as to why this happens. I hope that is also very clear. Then there is another question I looked at. I think I looked at this. This one I hadn't looked at it in the previous lesson, but I looked at this one here. This question is saying, I have a compound and then the boiling point in degrees Celsius. The first compound is chloroethane. Its boiling point is negative 24.0. The second compound I have here is this was chloromethane. This is chloroethane. Its boiling point is 12.5. The third compound is chloropropane. The boiling point of chloropropane is 47.0. The other compound I have is chlorobutane. Chlorobutane, its boiling point is 78.5. Now, the question is, state and explain the trend. State and explain the trend in variation or the trend in boiling points of the compounds. So you notice that in these compounds, what is varying is the chain length or the number of carbon atoms. And you also notice that the first one has a negative boiling point. That implies that it's being a gas. These ones, all of them are liquids. I want you to also note that since this is a gas and these are liquids, the molecules of attraction between them due to the low polarity of the carbon-chlorine bond are weak van der Waals forces. And you know the factors affecting the strength of van der Waals forces. Strength of van der Waals forces are enhanced or affected by, first of all, molecular mass and also molecular size. So what do I expect you to write in case you have such a question? You say boiling point increases from chloromethane to chloroethane to chloropropane to chlorobutane. So boiling point increases from chloromethane to chloroethane to chloropropane to chlorobutane. And then you say The reason is because, why am I mentioning each compound? This is not, what we are talking about here is not a period, it's not a group. We are not in inorganic chemistry, we are in organic chemistry. So we must specify each compound separately. So what is the reasoning here? The reasoning is that this is because the molecules are held by weak van der Waals forces of attraction. Actually, we say by van der Waals forces of attraction. Whose strength increases with increase, strength increases with increase in molecular weight and molecular size. So you notice that as the number of carbon atoms increases here, or as the molecular mass or molecular size increases, the strength of the van der Waals forces of attraction will also increase. So talk of the trend from which compound to which compound, talk of the forces of attraction and what affects their strength. That will give you around 2.5 marks. I want us to look at another question still about the physical property we are looking at, which is strictly boiling point. The other question that will be a good example about this is this one. This question goes, you have another compound still here, and then boiling point in degrees Celsius. The first compound I have is fluoromethane. The boiling point of fluoromethane is negative 78.4. The second compound I have is chloromethane. Boiling point of chloromethane is negative 24.0. The next compound is bromomethane. Boiling point of bromomethane is 5 degrees Celsius. And lastly, iodomethane. The boiling point of iodomethane is 43.0. From this, you notice that chloromethane is a gas. Even chloroethane is a gas. Chloromethane is a gas. These two are liquids. That is in terms of physical state from the boiling point values you see here. Now, can we explain the trend here? You'll notice that still we have boiling point increases. So what is our trend? Boiling point increases from fluoromethane to chloromethane to bromomethane to iodomethane. That is the trend that we do have. How do you explain that trend? You notice that the only difference here is in the halogen atoms attached to the carbon atom. And these halogen atoms have different atomic masses, which are increasing actually. Fluorine, chlorine, bromine to iodine. Secondly, their atomic radius also increases. And that leads to an increase in the strength of the van der Waals forces of attraction that continue to hold the molecules of these haloalkanes together. So what will you have to say? You have to say that boiling point increases from fluoromethane to chloromethane to bromomethane to iodomethane. Why? This is because atomic radius. Why am I talking of atomic radius and not ionic radius? All these molecules are covalent, so they don't form ions. I saw a mistake you were making when you're explaining strength of these acids. Yeah? Hydrofluoric acid, hydrochloric acid, bromic acid, and hydroiodic acid in your work in group 7. Don't talk of ionic radius of the halogen atoms here, because all those molecules are covalent. So you talk of atomic radius of the halogen atoms. So this is because atomic radius of the halogen atoms increases in the order, atomic radius increases in the order fluorine is less than chlorine, less than bromine, less than iodine. So atomic radius increases in that order. Molecular size and molecular mass. Molecular size and molecular mass of the alkyl halides also increases. Hence the magnitude of van der Waals forces of attraction. Also increases. So I'm very aware most of you would forget the fact of atomic radius, but you shouldn't forget it. So how will you be awarded here? Talk of the trend from where to where. Talk of the atomic radius increasing. For the atoms, don't write molecules. Don't make these molecules diatomic. Talk of the molecular size increasing, molecular mass increasing for the alkyl halides now. Then the strength or the magnitude of van der Waals force of attraction also increases. So that's how you'd explain the trend in the variation of boiling point in case what we are varying is the halogen atoms, not the carbon chain. Okay. Now, if we have aryl halides, boiling points of aryl halides correspond closely those with alkyl or comparable molecular mass. The other physical property I want us to look at, dear students, is the physical state of the alkyl halides. Let me look at most of these alkyl halides, beginning with chloromethane. Chloromethane, CH3Cl. Chloroethane and bromoethane are all gases, are all colorless gases. I think I looked at this, I'm just repeating it. But they are gases only at room temperature. The other members, the other alkyl halides, apart from those three I've mentioned, the other alkyl halides are all colorless liquids. With a sweet smell. They're all colorless liquids with a sweet smell. So that's all about the physical state. For any question, tap into my inbox on WhatsApp and tell me, or comment on this video. I'll be able to answer it. Don't forget to subscribe to this channel, Joseph Jobs Kaira Chemistry channel. Next to see is methods of preparation. methods of preparation. How do we prepare alkyl halides? It's going to be in our next video or in our next session.